superconductivity stands as one of the most striking discoveries of 20th century physics. In 1911, the Dutch physicist Kamerlingh Onnes, working in Leiden, cooled mercury to just a few degrees above absolute zero and made a remarkable observation: its electrical resistance vanished completely. A current once started in this ultra-cold metal could flow endlessly without loss. This discovery opened an entirely new chapter in physics, one that is still unfolding today. Superconductivity is one of the focal points of research today, with many claims being made and withdrawn. Traditionally, magnetism has been approached from the standpoint of preparation. Ferromagnetic materials are powdered, sintered in molds, and then exposed to a strong current or magnetic field to align their domains. But the central question has always gone deeper: what principle allows certain materials to retain magnetism, or to expel it altogether when superconductivity sets in? For almost 4 decades after Kamerlingh Onnes made his discovery in 1911, no explanation could be found for the remarkable property of superconductivity. In those intervening years, researchers uncovered other striking phenomena, most notably the Meissner effect in 1933, the expulsion of magnetic fields from the interior of a superconductor, but the underlying mechanism remained elusive. It was not until 1957 that John Bardeen, Leon Cooper, and Robert Schrieffer published a theory that accounted for the essential features of the phenomenon. Their work, which became known as the BCS theory, provided the first widely accepted explanation of how superconductivity arises. According to the BCS theory, superconductivity arises because electrons near the Fermi surface do not move independently but form pairs, now known as Cooper pairs. These pairs are bound together by subtle interactions with vibrations of the atomic lattice. Though each electron carries negative charge and would normally repel the other, the lattice mediates a weak attraction that allows them to couple. Once paired, the electrons move in a highly ordered, collective state that flows through the lattice without scattering. It is this pairing mechanism that explains both the complete disappearance of resistance and the emergence of a macroscopic quantum state in superconductors. In 1957, when Bardeen, Cooper, and Schrieffer introduced their theory, there were no alternative explanations for the flow of an electric current. It was universally accepted that electricity was carried by electrons, and the BCS theory, for all its novelty, still relied on this basic paradigm. What it added was the idea that electrons could form pairs, bound together through interactions with the vibrating lattice, and that these pairs could move without resistance. This interpretation became the cornerstone of the conventional understanding of superconductivity and continues to be used today. It is here that augmented Newtonian dynamics offers a new explanation. In this framework, superconductivity is not an exotic quantum state described by abstract wave functions, but the natural outcome of perfect order. At low temperatures, electrons exchange conduction photons in tightly closed cycles, with no leakage into the ether and no formation of external lines of force. Electricity flows as a sequence of bound interactions, and the magnetic field is expelled, the celebrated Meissner effect. This, according to an theory, is the physical principle underlying superconductivity. In augmented Newtonian dynamics, the answer to the question of the principle of magnetism and superconductivity becomes clear. Under normal conditions, a free electron cannot emit or absorb a real photon, because the resultant recoil would be impossible to accommodate or resolve. The electron's motion would collapse into chaos. However, the Heisenberg uncertainty principle, as it applies to energy and time, provides a way out. If the emission and reabsorption of a photon takes place quickly enough, the electron can sidestep the recoil altogether. For a fleeting instant, the strict laws of energy and momentum are temporarily suspended. Conditions of neutrality are strictly maintained inside a conductor. If there is any imbalance of energy, it has to be immediately addressed. When a difference of potential is established across the ends of the conductor, free electrons within the conductor lattice begin to emit and absorb what we call conduction photons, moving from the negative to the positive terminal. Conduction photons are the lowest energy photons an electron can emit. In augmented Newtonian dynamics, the flow of electricity in a conductor is sustained by electrons that continually emit and reabsorb conduction photons, the lowest energy photons an electron can release. Under normal conditions, millions of conduction electrons move through the lattice at speeds approaching 10 to the power of 6 meters second. According to classical rules, an isolated electron cannot emit a photon without violating momentum conservation, since there is no sink for the recoil. However, the energy-time form of the Heisenberg uncertainty principle, HUP, provides a narrow allowance. If emission and reabsorption occur within about 10 to the power of minus 15 seconds, the conservation laws are temporarily suspended, and the process is permitted. The traditional textbook description speaks of electrons drifting slowly through the lattice with an average velocity of only millimeters per second when a potential difference is applied. In and theory, this drift velocity is not the cause of current, but simply the small residual effect that remains after the recoil forces of photon emission and absorption nearly cancel out. In alternating current, the picture is even clearer. The electrons exhibit no net drift at all, but oscillate in place, while the current still flows, appearing frozen in place. This makes plain that the true mechanism of conduction lies in photon exchange, not electron drift. In the chaotic environment of a conductor at room temperature, not every photon finds resolution with the same electron that emitted it. Often, it is absorbed by another electron, and in some cases it cannot resolve internally at all within the required time. When this happens, the photon exits the conductor and loops back, seeking a receptive electron. As it leaves, the virtual photons of the ether, the pervasive medium of dark matter photons, align themselves along its path. This alignment creates the lines of force that appear around current-carrying wires and magnets. In and theory, these lines are not incidental. They are the structures that allow conduction photons to complete their cycles when immediate internal resolution is not possible. Superconductivity arises when such external pathways are no longer needed. At very low temperatures, thermal agitation is suppressed and the lattice achieves a high degree of order. Under these conditions, every conduction photon is absorbed internally within the conductor. No photons escape into the ether, and no external lines of force are formed. The energy of the current is confined entirely within the conductor. This directly explains the Meissner effect. A superconductor expels magnetic fields not by exotic quantum states, but because, with no unresolved photons escaping, there are no external field lines to sustain. The beauty of the augmented Newtonian dynamics theory of superconductivity lies in the fact that it explains lines of force not as intrinsic entities, but as the byproduct of faults or distortions in the conduction process. When seen this way, superconductivity is no longer mysterious. It emerges naturally as the ordered limit of the very same mechanism. Thus, in theory, superconductivity is the natural state of an ordered conductor, a regime where conduction photons circulate in perfect cycles entirely within the lattice, producing a current that is both lossless and enduring. In matter, structure is everything. The way atoms are arranged and the manner in which their electrons are bound determines how a material responds to energy, whether it behaves as a conductor, an insulator, or a permanent magnet. Superconductors are no exception. Their ability to sustain lossless currents is rooted in their structure, both at the level of the lattice and at the level of the electronic states it permits. According to augmented Newtonian dynamics, superconductivity occurs when a material is cooled below its transition temperature and an electric current is applied. In this regime, conduction photons are absorbed and re-emitted only by bound or engaged valence electrons. No free, chaotic electrons contribute to the current. Instead, every electron participates in a highly ordered cycle of emission and reabsorption. Electricity in this state is not the slow drift of loose carriers but a continuous sequence of closed photon loops linking electron to electron within the lattice. Because all conduction photons resolve internally, no external lines of force are formed, the energy of the current remains entirely confined within the conductor. Experimental observation supports this framework. Superconducting materials are often heavy elements or complex compounds with many valence electrons, most of them well bound, though some are shared between atoms in hybridized orbitals. These engaged electrons, neither entirely localized nor completely free, provide the channels required to absorb and emit conduction photons in strict cycles. The result is a perfectly ordered system in which chaos is absent and the Meissner effect follows naturally. With no photons escaping into the ether, the external magnetic field is expelled. When a superconductor is cooled below its transition temperature and a current is applied, the flow of energy is not carried by free, chaotic s electrons drifting through the lattice, as happens in copper or silver. Instead, it is carried by electrons that are structurally engaged with the lattice, often p electrons, d electrons, or hybridized states that straddle two orbitals. In the superconducting state, these electrons form a perfectly ordered network. Each conduction photon is emitted and immediately absorbed by another electron, creating a continuous chain of closed interactions. Because all photons resolve internally, no external lines of force appear. The current is confined entirely within the conductor, and the Meissner effect follows directly. The materials that exhibit superconductivity reflect this structural principle. The noble metals, copper, silver, and gold, are excellent normal conductors but never become superconductors in bulk. Their electrons are too free, with too few internal absorption pathways. By contrast, heavy elements such as lead and tin possess additional p electrons that interact strongly with neighboring atoms in their dense crystal lattices. Niobium, a transition metal, goes further by bringing both d and s electrons into play, creating still richer networks of emission and absorption. And in the so-called cuprates, lead copper oxide compounds, as well as in magnesium diboride, complex hybridized states provide a dense web of channels, enabling superconductivity at much higher temperatures. Thus, in the augmented Newtonian dynamics interpretation, superconductivity is not favored by the presence of maximally free electrons, but by lattices in which multiple orbitals overlap and engage. These bound yet interactive electrons create the ordered photon exchange network that defines the superconducting state. Josephson junctions are extraordinarily sensitive to currents and magnetic fields. Even the smallest variations in current can shift their quantum phase, making them powerful detectors of magnetic flux. In modern physics, they have become indispensable tools, from ultrasensitive squid magnetometers to the frontier of quantum computing, where Josephson junctions are used as core bits, the fundamental units of quantum information. In this way, superconductivity does not end with the expulsion of magnetic fields or lossless current. It extends into the possibility of new technologies, where quantum states are engineered and controlled with extraordinary precision. Superconductivity remains one of the most profound and fascinating phenomena in physics. From Kamerlingh Onnes' discovery in 1911 to today's high-temperature compounds, it has challenged our understanding of matter and energy at the deepest level. In augmented Newtonian dynamics, superconductivity is no longer an exotic quantum mystery, but the natural state of a conductor brought to perfect order, a regime where conduction photons resolve entirely within the lattice, creating a current that is both lossless and enduring. The Meissner effect, far from being an inexplicable anomaly, emerges as the direct consequence of this perfect internal balance. The implications are immense. Already superconductors have enabled MRI machines, particle accelerators, quantum sensors, and maglev trains. Looking forward, their potential reaches further: power grids that transmit energy without loss, storage rings that sustain currents indefinitely, and perhaps new architectures for computation and communication. The science of superconductivity is not finished. Every new material discovered, every higher transition temperature achieved, is another step toward harnessing this extraordinary state of matter. For in theory, superconductivity is not just a technical marvel but a profound confirmation of principle, that structure and order govern the deepest interactions of electrons and photons. It suggests that by understanding these principles more fully, we may open the door to new classes of materials, new technologies, and even new physics.